start the discussion. Okay. Now we have done up to acid-base titrations. Okay. Gravimetric I summarize. After completing all three titrimetric types, I will summarize again. Yesterday, if I summarize the acid-base specific things, that what you have to remember is that, okay, you know there are 4 conditions to be satisfied for any titration. Okay. And out of that, okay, if I recall those things, this titration reaction should be fast, stoichiometric, delta G should be high negative, and there should be an indicator to detect the endpoint. Those things should be satisfied. And delta G can be expressed in 2 ways. That is, how? That is, delta G is equal to minus NF E naught if it is a potential change. Otherwise, delta G is equal to minus, can anybody tell?
RT into ln formational constant K dash.
K.
Conditional formation constant.
Yeah. Formation constant of anything. If it is acid base, we are talking about formation constant of water in acid base. But when we say K dash, conditional. Okay? Right. So redox, in redox titration only, we are talking about minus E naught
NF.
minus yes, minus NF E naught, right? NF E naught. Okay, you are very clear about that. Apart from that, any titration, you have something in the flask and you have the other one in the burette. So, all the time in a titration, 2 variables are there. Variable is what? Something is changing during the titration. There are 2 things changing. One is all the time the volume that is going to be added from the burette. Okay? And the other parameter is the changes that is taking place in the solution in the flask. Okay? If it is acid-base titration, all the time we are talking about H plus and OH minus reaction. So it's related to pH. Therefore, the variable in acid-base titration is pH. That's going to change. Okay. Then complexometric, we are going to talk now, right? It's PM, minus log metal ion concentration. Then in redox titration, it is potential E naught, or with the condition E naught dash. Those are the 3. So I'm telling this, it's very easy, right? You have a very, take a big paper and have 3 columns of 3 titrimetric types. Then you one by one, there are common things, there are deviations, right? You can write. Nice comparison. Easy to remember. Okay, right. Then Okay, coming back to conditional formation constant, conditional formation. In acid base, it will be what? Conditional formation constant Kf. Kf double dash, that is equal to Kf into Ka into Kb, acid base. Okay. In complex symmetric, Kmy dash is equal to Kmy into alpha y4 minus and alpha m. Then redox E naught dash. Okay, that's going to be what? Delta E naught dash is going to, delta E dash is going to be equal to E naught dash, delta E naught dash minus RT, sorry, minus RT, yes, concentration of the product over by the Nernst equation, right? You're going to write for half equations, right? You will remember when you have these all three types in one paper, and when you read that session, then you will be getting the answer. Okay, if in acid base this is there, but in complex symmetric this is like this. Then in redox this is like this. Then you will get the answer, right? Very easily. Then the titration curve. Draw the titration curves for all three, right? Then you will remember. Okay. Then are there any way, short ways to find out the end point? If there are any equations, write those down. Then indicators. Okay. What are the special indicators? It depends on in acid-base types. Then in complex symmetric, most of the time we are talking about area chrome black T indicator. Then in redox, we are talking about redox indicators or phoidometry starch. So likewise, you build up your own note in a very, very concise way, summarized way. So that will be the best. Then you come to the stepwise titration, selectivity. How do you achieve selectivity? In acid base, K1 over K2, it should be greater than 10 to the power 4. Then in complex symmetry, we are going to talk about the selectivity. Can be achieved by either pH control or by using masking agent. Then in redox, again, the two cells are there, two total reactions. Selectivity is two things are going to be titrated. So there will be one reaction. One will be titrating first, but with what you have in the burette, then the next one. Whether that can be achieved, or whether both are going to be titrated together. In redox, so the E naught difference of the two analytes should be greater than point, but for visual titration, greater than 0.4 volts. Okay, so when you build up that, compare the thing easy, and then you can have a very good understanding. Okay, students, can you hear me? Yes or no?
Yes, madam.
Okay, so now itself get together. Okay, I mean, you start it, I'm sure you're going to get a very good understanding on that. And remember, this can be applied for anything, even for book number unit 3, chromatographic methods, have different methods. Okay, thin layer, ion exchange, then paper chromatography, then you have electrophoresis, different types. Okay. Then tides, reverse phase, okay. And whether they are okay. What is the basis of separation? Mechanism. Have in all, you will remember. And what are the common things? Polarity is common. Okay. All the polar things attract to polar. Reverse phase, if you say reverse phase, whether it's TLC, whether it's polar, or whether whatever, reverse phase is reverse phase. Okay, right? So then how can you achieve more separation? All those things are very common. You can have a nice. In instrumental also, okay, you are doing just one spectroscopic method, UV visible, that's unique, but you are doing conductometry, you are doing potentiometry, right? I think those are the two, no? If I remember correctly, two titrometric methods. You can again compare the two and get a good idea. Okay, right. Let's start the EDTA titration. Okay, I hope you have done this. Okay, what is this question? A 25 ml sample containing the metal ions Mn2 plus and metal ion Mn2 plus was titrated with this. And the formation constant is My2, Y is EDTA, is given. Then the question, what is the most suitable pH to carry out the titration? Justify your answer. Two parts. It's asking what is the most suitable pH and justify. Okay. Did you do? Can anybody answer? Give me the answer.
It is
Are
pH
you there?
7, madam.
Yes. What is it?
pH 7.
pH 7. Okay. Correct. Other first part. Justify.
In pH 7, madam, alpha Y4 minus is high comparable to the pH 5. Then according to the equation, we can get high conditional formation constant value at pH 7.
What is the equation?
Km dash K dash M dash Y dash equal KMY into alpha Y4 minus into alpha M2 plus.
Very good.
Then Gibbs free energy is equal minus RT ln K dash M dash Y dash. So if the conditional formation constant is high, we can get high Gibbs negative value for Gibbs free energy. That's mean we feasibility of the reaction is high. So we can say that a suitable pH is 7 for this titration.
Very good. You have given a complete answer. Okay. So you can't just stop at showing that the KM dash is high. You have to say what is the benefit of having a higher KM value. That will be the complete one. With the higher KMY value, you have to give the relationship of delta G. Then why it is important to have a higher negative delta G? Because the feasibility is high. Okay, right. That's a very good answer. Good. So now by looking at these, do you have to show the calculation of anything? Am I asking for any calculation? No. Look at this. I am not asking you to calculate and show. If you just say, even if you calculate, it doesn't matter, right? But it's very clear. If I ask you, justify your answer with proper calculations, then definitely you have to calculate and show. Okay, right. Let's look at the answer. Takes some time in my case because, you know, the computer is right. pH7. This is the equation. Higher the conditional formation, higher will be the vertical portion or the accuracy of the endpoint detection. Because we actually now I have written this. This is in between. It is coming. Higher the conditional formation constant, higher will be the feasibility. But I gave marks for these things as well. But correct one is higher will be the feasibility. Okay, right? Okay, let's move on to the other one. If the endpoint obtained was 25, calculate the M2 plus in equilibrium after 10 ml of EDTA was added. Did anybody do this? Kaurari make a karada? Yes
Yes,
or
madam.
no? Yes, very
Yes,
good.
madam.
Okay. Now, when you read the question, okay, you have to get an idea. Endpoint is 25. So they are not asking about the endpoint thing, but before that, the M2 plus in equilibrium, they're asking. That is, they have added only 10 ml of EDTA. So draw the appropriate picture so that you will not be confused. I have drawn that to you, like you drawing. Before starting, you had M2 plus only. Maybe other ions are there, but M2 plus we are interested. Then we don't know the concentration. Okay, right. Then after adding 10 ml of EDTA, this reaction is taking place. Okay, so what do you have now? Volume is changed, it's 35. M2 plus is not what you had at the beginning because it had undergone this reaction forming My2 minus, and now in the solution you have My2 minus also. I put it as My. Okay, right? Now current, only the total volume after adding 10 ml only we know. We don't know how much M2 plus is there and how much of My is there. But now the question they are asking is, after adding 10 ml, what is the M2 plus in equilibrium? Okay. Now, just tell me, okay. Now, after adding 10 ml, has all M2 plus formed My2 minus?
No, madam.
No, right? Only a part has formed My, right? So, and that My is also in equilibrium. Okay, please write down the equilibrium. Now, already I have started writing the equation, right? M2 plus Y4 minus and My2 minus. Okay, so that's in equilibrium, right? So at the very beginning, write what you have, M2 plus. Now, for any equilibrium, now, how do you calculate the equilibrium? The concentrations in equilibrium with the equilibrium constant equation. Okay, what is the equilibrium constant here in EDTA titration? How do you call it? If it is a dissociation reaction, dissociation is equilibrium. In equilibrium, we call it as dissociation constant. This is, we are talking about a formation. So it's a, this formation reaction is equilibrium. We are talking about that. So it's a formation constant. With the help of that only, we can calculate the concentrations in equilibrium. Harida, got it?
Yes, madam.
Okay. Can you write down the equation for equilibrium constant? KMY, all of you? Leave other, those who have tried this?
Yes, madam.
KMY is equal to concentration of products over concentration of reactants. Okay, let's look at that. I do not want to show the answer without you thinking. Okay, asking about something to do with equilibrium, any concentration. So you have to write down the equilibrium reaction and also the equation of equilibrium constant. Okay. Now, we have talked about the conditional formation constant. Conditional. So it's not KMY, it's K dash M dash Y dash. Because at the very beginning, we told that, okay, side reactions are there. So you have to write down the equation for K dash M dash Y dash. Okay, K dash M dash Y dash, okay, is equal to M, this M by 2 minus concentration over M2 plus concentration into Y4 minus concentration. Okay, right. Okay, right now, okay, this is how you should do, but since we have already started, okay, now look at this. This is the equilibrium reaction, and this is the equilibrium equation. But now remember, this will be, if it is K dash M dash Y dash, then this is going to be Y2 minus over M2 plus. Okay. How can I correct it? Just give me, okay. Please work it out. Can you just give me, there is, I have typed it in a wrong way. Just give me 1 second to correct it and come back to you. But just a minute. Difficult to correct it. I'll put it just as M. Okay. Okay. Right. Now this is the equilibrium constant equation, formation constant equation, right? And I'll put this, I have put this M2 plus as M because it was difficult for me to type here. And this Y4 minus like this, right? And this M by 2 minus like this, right? Uh, Now here, when you are calculating K dash, M dash, Y dash, all alpha values are coming into this picture. Do you understand this? තේරෙනවද ඔයගලන්ට?
Yes, madam.
Okay. So now in the question, we are asking about the M that is in equilibrium, this part, this M. Okay, right. So if you know this K dash, M dash, Y dash, if you know My2 minus produce, if you know Y, the amount of Y, then it's very easy to calculate M. Okay. Now, so now, okay, how are we going to find out this? K dash, M dash, Y dash, we can find, tell me a way of finding K dash, M dash, Y dash. මේක කොහොමද හොයාගන්නේ? One by one will go. How do you find? K dash, M dash, Y dash කොහොමද හොයාගන්නේ? This is the equation we have to use. So this M only they are asking. If you know the other things, you can calculate M. So we'll start with this. මේක කොහොමද හොයාගන්නේ? Can anybody answer?
But then they given that km value, alpha values, so then we can calculate k dash value.
K dash value. Very good. At pH 7.
Oh.
Take from the table and calculate. Okay, that's done. Then how do you calculate the M by 2 minus? How much is produced? How can you calculate? කොහොමද දැනගන්නේ?
We know that, madam, EDTA concentration and volume. Then we can calculate EDTA moles, number of moles of EDTA. Stoichiometric is 1 to 1, so that number of EDTA moles equal to number of moles of My2 minus. Total volume is 35 cubic centimeter. C equals N over V. So we can find concentration of My2 minus.
Very good. Right. So that you can calculate. Okay? Because like she said, My2 minus we know with 10 ml of 0.2 EDTA, how much of EDTA we have added. Okay, that all EDTA with 10 ml have reacted with M2 plus and the product you can calculate. Okay, so then now, right, now apart from the, now why we wrote this equation, why? Because all the time when you are writing the equilibrium equation, we think that in equilibrium, a small amount, the product from the product, a small amount is going back and it's staying, going for the backward reaction, right? So then you have to, with considering that, with that only you have to write down the equilibrium concentrations at that situation. So now you know the product that is formed. Okay, we can get it. It is 0.2 into 10 to the power minus 3. I'll show you the other slide. The product that is formed is this is okay with 10 ml the product, right? Okay, and like said, you can calculate it with 10 ml, 0.2, 10 to the power minus 3 into 10, it will be, right? So this is the amount. From that, X amount is in equilibrium. So, but in the flask, you don't have any excess Y4 minus. You have added 10 ml and all that 10 ml had reacted with M2 plus. So it's only the amount, X amount is in equilibrium that is coming for the reverse reaction in equilibrium. But the same amount will be coming and for the M2 plus and joining with the M2 plus that is remaining unreacted M2 plus. You have to have that in mind. So how to calculate the unreacted M2 plus? To calculate the unreacted M2 plus, first you have to know how much had been there at the beginning and how much had reacted. So how do you calculate how much had been there at the beginning? How do you calculate? Over the calculate current. M2 plus beginning ekedi. At the very beginning, how much you had? Can you tell?
They given that end point, madam.
Very good. End point is given. It's 25. So with the end point, you can calculate how much M2 plus number of moles is present. Okay. So we have calculated the number of moles of VDTA used for the endpoint. Then therefore same amount. Okay, same amount is there. M2 plus. It's simplified here. Okay. Then we know how much is reacted because EDTA added 10 ml, that much of M2 plus is reacted. So number of moles of My form is there. Same number of moles is reacted. So the remaining will be what you had at the beginning and how much had reacted. The difference. So you have to show the difference and this much is remaining. 0.3 into 10 to the power minus 3. And for the remaining one, the X amount that is going backward reaction is being added to the remaining. So after adding 10 ml, this is the situation of the number of moles that you are having. Okay, so you have to, now you know about these things you have found. Now you have to substitute with the concentration. Concentration terms. What is the concentration? Number of moles divided by the volume. Okay, right? So the volume you have to have in mind. I mean, it should be of the same units. And volume, it's better if you can go for liters, then straight away the M value is coming. Okay, so I mean the possibility of doing errors is less. So we'll have the volume in terms of liters. So you have number of moles divided by 35 milliliters, that is in liters, 0.035 liters. Y4 minus X divided by 0.035. My2 minus this whole thing, this much minus X divided by 0.035. Okay. Right. Now you have that. Okay. Right. You have this. This is again, I have to change this. Right. Then you substitute. And here you have this. Then the calculation of K dash M dash Y dash. Okay. At pH 7 you have done. Then so K dash M dash Y dash you know. Okay. My2 minus concentration also. Okay. That's after division. This is the simplification equation. You come to this. The same thing is there. Okay. So here you have to make some assumptions, like in all the equilibriums. That is, this is 0.2 into 10 to the power minus 3 minus x is, you have to ignore the x. That assumption you have to write. Okay. So, and x squared, x is very small, so x squared will be very, very small. So that is also 0. Those two assumptions you have to write. After writing, then you simplify this into this. Those are mathematics. So you have only one, V is 0.035. So only term that you do not know is X. You can get the X value. Right? Okay. Now, by doing this, we are showing that X value is very, very small. Right? Okay. So X value is very, very small. Therefore, here, therefore, it's almost like this. But without doing this, you can't just tell that it is this. Right? You have to show that X value is very, very small. Then, now you must not forget that we are talking about the M plus concentration in equilibrium, not just X. Okay, so M plus concentration is, this is just number of moles. Okay, metal ion amount in equilibrium. That is the, we got the X value. Metal ion amount is what? It is 0.3 into 10 to the power minus 3 plus X. So since X is very small, this is a metal ion amount, and the concentration divided by V, this is the answer. Did you get the answer? Anybody?
Yes, madam.
Very, very good. But
Madam,
remember, yes.
madam, madam මුලින් concentrations calculate කරලා equilibrium එකේ තියෙන concentration එක x කියලා අරගෙන හැදුවේ. ඒ කියන්නේ moles වලින් නැතුව concentration එකෙන්ම. එහෙම කරාට ප්‍රශ්නයක් නෑ නේද madam?
එහෙම කරාට ප්‍රශ්නයක් නැහැ. හැබැයි වැඩේ වෙලා තියෙන්නේ, එහෙම ඔයා පුරුදු වුණොත් ඔයාට අමතක වෙනවා. දැන් ඒකේනේ total එකනේ. නේද? එතකොට ඔයා කොහොමද ඒක කරේ? එතනදී සමහර වෙලාවට එතකොට ඔයාට මේ උත්තරේ ආවද?
ඔව් madam. එහෙම නෙමෙයි madam. ඒ කියන්නේ දැන් excess තියෙන m moles ගාන 0.3 into 10 to the power 3 නේ madam.
excess කියන්නේ excess m unreacted m කියන්නේ එච්චරයි. 0.3 into 10 to the power minus 3. හරි.
ඊට පස්සේ ඒක මම මේ total volume එකෙන් බෙදලා excess තියෙන concentration එක ගත්ත මැඩම් මුලින්ම.
හැබැයි
ඊට
ඒක බෑනේ
පස්සේ
පුතා, එහෙම බෑ. ඒක බෑ. මොකද ඔයා ඉක්විලිබියම් කියපු ගමම හැම වෙලේම අර
නෑ
ප්‍රොඩක්ට්
මැඩම්
එකෙන් රිවර්ස්
එහෙම
රියැක්ෂන් එක එනවා කියලා පෙන්නුවද?
ඔව් ඒ කියන්නේ මෙහෙමයි මැඩම් මුලින්ම ඉක්විලිබ්‍රියම් එකට කලින් මෙහෙම එක්සස් තියෙනවා කියලා පෙන්නුවා මැඩම් myත් මෙහෙම හැදෙනවා කියලා. ඊට පස්සේ ඉක්විලිබ්‍රියම් ඉක්වේෂන් එක ලියලා ඉක්විලිබ්‍රියම් එකේදී x කන්සන්ට්‍රේෂන් එකක් y තියෙනවා නම් ඉක්විලිබ්‍රියම් එකේ තියෙන m2+ කන්සන්ට්‍රේෂන් එක අර කැල්කියුලේට් කරපු ගාන ප්ලස් x කියලා අරගෙන my කියන්නේ අරතන කැල්කියුලේට් කරපු ගාන මයිනස් x කියලා අරගෙන මේ විදිහටම ඉක්වේෂන් එකට දාලා assumptions දෙකත් ওই විදිහටම ලියලා එතනින් කැල්කියුලේට් කරාම නම් දැන් මෙතන අන්තිමේට මෝල්ස් ගාන අරගෙන කන්සන්ට්‍රේෂන් එකෙන් බෙදුවහමත් මම අතනින් අත්තහමත් ඊට පස්සේ x ඒ කියන්නේ ඉක්විලිබ්‍රියම් එකේ තියෙන කන්සන්ට්‍රේෂන් එක ආවේ මට 5.37 into 10 to the power minus 9 ඒකල ඒක ඉක්විලිබ්‍රියම් එකේ තියෙන එක මෙහෙම මේ කැල්කියුලේට් කරාම 8.57 into 10 to the power minus 3 plus x කියලා දාලා x අර ගොඩක් පොඩි නිසා ඉක්විලිබ්‍රියම් එකේ තියෙන ගාන 8.57 into 10 to the power minus 3 කියලා දැම්මා මැඩම්.
හරි. ඔයා x හෙව්වද?
ඔව් මැඩම්. x
x
හෙව්වා.
x කැල්කියුලේට් කරලා හරි. එහෙනම් කමක් නැහැ. මොකද ගොඩ දෙනෙක්ට වැඩේ වෙලා තියෙන්නේ සමහර වෙලාවට ඒගොල්ලන් මේ මුලම assumption එක කරනවා x මුලම ඉඳන්ම පොඩි කියලා. එහෙම අපි assumption එකක් කරනවා තමා. හැබැයි ඒකේ validity එකක් තියෙන්න ඕන. හරිද? කෙනෙක් අහන්න පුළුවන් ඇයි මේ ඉස්සෙල්ලත් -x කියන්නේ පොඩි කියලා හිතලා x අයින් කරා නම් ඇයි මේක x අයින් කරන්නේ නැති කියලා. එහෙම වුණොත් ඉතින් අපිට මේක උත්තරයක් හදන්න දෙයක් නැති වෙනවා. හරිද? got it? so දැන් ඔයාට ඒක අමතක වෙන්නේ නැතුව ඔයා තේරුම ඇතිව එහෙම කරා නම් no problem. හරි. එහෙමනම් හරි. okay.
ඔව් thank you මැඩම්.
හරි. okay. මම හැම වෙලේම අනික් එක වැඩ වෙලා තියෙන හැම වෙලේම අර ෆන්ඩමෙන්ටල්ස් වලින් යන එක ගොඩාරියක් හොඳයි. නැත්තම් V අමතක වෙනවා. හරිද? හැම වෙලේම V කියන එක concentration කියන එක ඔළුවේ තියාගන්න. right? okay, good. Any more questions? Okay. Right. Comment on the statement below. Comment. It is not asking whether it's, do you agree? Whether it's correct? None of that. Comment. Open discussion. Comment. It can be true, it can be false. Just comment. Okay? So, the interference in EDTA titration is very high, but can be avoided. Now, sometimes students start answering, I agree with the statement. Okay, but that will not carry any marks. Because it's not the question that I'm asking. I'm asking the interference. There is a statement given. So, according to the statement, you have to give. I mean, you have to criticize it. Right? Okay, the interference in EDTA titrations is very high, but can be avoided. Okay? So, sometimes, I mean, now in this case, okay, both the two parts are there. Can you see there are two parts? They are talking about the interference, and it's very high, but can be avoided. Those two sections has to be touched in your description, right? So it can be something different that totally wrong. So if the question say comment, you have to just tell why you say that it's totally wrong. But if you are agreeing, you have to tell why you are agreeing. But saying that I am agreeing will not carry any. Okay. So what did you write? Can anybody tell? the interference in EDTA titration is very high. What did you write? Can anybody tell? Others are not joining. Why? You just tell. Don't get scared. Okay? We are learning. Anybody? Can anybody tell what did you write? The interference in EDTA titration is very high. What did you write? Tell. The girl who is speaking. And what is your name?
Hansi, madam.
Hansi.
Yes, madam.
Okay, Hansi. Okay. Hansi or anybody? Can you tell me what is your answer?
EDTA can react with many metal ions. So if the metal ion present in the solution other than analyte also complex with EDTA. So the interference in EDTA titration can be very high. This can be avoided by controlling pH. Many metal ion forms EDTA complex at certain pH only. So we can avoid interference by controlling the pH of the medium. Also using masking agent, example Cn minus, F minus, phosphate, selective precipitate and ion exchange.
Okay, very good, Hansi. Okay. But the thing is this, now, when you are writing that, now, if you spend a lot of time unnecessary, you are going to waste your time. It's just 10 marks. And now remember all the time, now, if I ask the same question, explain the statement below, giving examples. That is different. Okay, so it's just comment, right? Giving example is okay if you have time. Okay, so you write the answer, the necessary things, then keep some space and go to the next question. And if you get more time, then you can add on to it. Because no one is going to cut your marks, right? So you have to
Okay,
tell,
madam.
okay, do you understand this? Harida, Ternada.
Yes, madam.
Most of the time in my questions, I am very clear about, focused about the expected answer. The interference of EDTA is very high. Why? Because EDTA reacts with many metal ions. Okay. Then it can be avoided by two ways: controlling pH and using masking agents. That's enough. Okay? Right. Okay, good. We'll move on to the next one. Right. Now we are moving on to the next part, redox titration. Okay. Right. Okay. Now, EDTA, in EDTA titrations, okay, what are the things that you should remember before starting the redox? What are the specific things in redox titrations that you should remember? Okay. Usually with, complex symmetric titration. Complex symmetric titrations are done for metal ion determination. And complex answers are formed. So the formation constant plays a very major role, KMY. And that can be changed with the condition because of the side reactions. Okay, so the alpha value is giving you an idea about the amount of side reaction taking place. So the calculation of conditional formation constant, there's a formula with alpha. So if the conditional formation constant is high, it's good. And wherever possible, you have to calculate the conditional formation constant. Okay. Then the complexing agent that we are talking about, the common one is EDTA. You have to know the characteristics of EDTA, right? EDTA. What are the other possible forms of EDTA, ionized forms that can have? Okay, Y4 minus, right? HY3 minus, and so on. So this EDTA, usually it's Y4 minus we are targeting at for the reaction. So at high pH, you get more Y4 minus. Okay. Then, but all the time you can't have high pH because uh, uh, all the time it's, the complex is sometimes forms an ion. So pH, depending on the pH, the optimal pH only, it's going to react with EDTA, right? You don't have to memorize the pHs, but when a pH is stated, you have to get an idea. You have to get some idea that we are talking about the optimal pH. Okay. Then, okay, with this, there can be direct titration, then there can be back titration, there can be indirect titration. Okay, right. Then for the most of the time with EDT, we are using Eriochrome black tea as the indicator. Then the characteristics of that are important. Right. Then what are the changes taking place? One variable is, like all the other titrations, what you have in the burette. Other variable is what? The metal ion. Okay. Now in the flask here, all the time, the metal ion, the amount of metal ion is going to be changed. It's going to be lower and lower and lower. So it's very difficult to write very small amounts. Therefore, we have introduced it as P, minus log value, like pH, PM. So the titration curve is between PM y-axis and the amount of solution that you have added from the burette, x-axis. Okay, right. So the stoichiometry, irrespective of the valency of the metal ion, it can be 1 plus, 2 plus, 3 plus. It's all the time 1:1. Okay. When the direct titration is not possible due to various reasons, we go for back titration. The calculation involved is simple, but if it is back titration, little bit complicated. That you should know. Right? So these are the things that you have to remember in EDATA titration. Calculating of equilibrium concentration is the same for anything. Any equilibrium, it doesn't have to be titration. Okay, for anything, you calculate in the same way. Okay, now we'll move on to the redox titration. Okay, now here you have a sample solution and that is X4 plus, you have added excess of Z, right? Then the resultant solution was titrated with A2 plus, right? Now what is happening here? For X, you have added Z. Will there be a reaction taking place? How do you know? Number one, for a reaction to take place, redox reaction, one should oxidize and other one should reduce. That is the first condition that you should look into. If both are in oxidized states, no reaction. If both are in reduced states, no reaction. Okay. Now, X4 plus, it can undergo reduction. Then you have added Z plus. Okay, Z plus can undergo oxidation. Okay, so it's X4 plus and Z plus. Okay, the reaction, oxidation states are agreeable for a reaction to take place. Right, look at the feasibility. Now, okay, look at the E0 value difference. For that, you are writing down the equation in the reduction way, same manner, easy to calculate. So these two, you get a positive value for E0. So delta G will be negative if delta E0 is positive. So reaction is taking place, that is X Z is formed. Don't worry about the valencies. XZ is formed and Z2 plus in excess. Now remember, okay, I might give you a question where you add Z plus, but you add Z2 plus. Then what will be the situation? Can you tell me? Make the add කරන්න Z2 plus නම් what will happen?
No reaction is take place, madam.
No reaction is taking place. X is there, Z is there. You have to be very, very careful. Then totally different answer. Okay, right. Then you are allowing it to react with A2 plus. Now what? What is taking place? We assume that XZ is stable because stability constant values are not given here. So we have to assume. With that assumption, you don't have X to react A2 plus, but you have only Z. Z and X, again, look at the status. Are they in correct oxidizing states? Z2, Z plus can be oxidized. A2 plus, is it A2 plus? Okay, A2 plus. Again, it is going to be oxidized. So this is an error. There is an error in this question. Do you see the error?
Yes, madam.
Yes. So I have to correct this. Just give me a second. Sorry, I just wrote the question, but without thinking. Just give me 1 second. I'll just correct it. Should be A3 plus. Now it's correct. Sorry. Okay. Did you notice the error? වැරද්ද තේරුණාද කලින්? හම්බුණාද ඒක
Yes,
when you are trying to do it?
yes, madam.
Okay, good, good. I just quickly add the question, but added the question, but I didn't note it down. Okay, now I have corrected it. Now, okay, now A3 plus can reduce, Z plus can oxidize again in the correct form. Okay, Right. Okay. Now what is asking? Then the endpoint obtained is there. Right? What is the question asking? Give one possible reason for not titrating X4 plus directly with Z plus. What is the answer? You just added Z plus to the flask and waited. Why didn't you do a titration? What are the answers?
Reaction can maybe slow, madam.
Reaction is slow. What else?
There is no suitable indicator.
Very good. There is no suitable indicator. Can you say that it's not feasible?
No, madam.
No, it's feasible. There's a reaction taking place. E naught values are there. Feasibility is there. Then can you tell that it is not stoichiometric? No.
No, madam.
Without, if it is not stoichiometric, we can't do this calculation. So it's stoichiometric. So only two possible answers are there. If you write one, okay. These are the two. Just one we are asking. Right. Then write the balance equation for the feasible reaction that have taken place, showing that they are feasible. Calculate the concentration of X2 plus. Okay. So you have to write the balance reactions taking place, showing that they are feasible. So you have to write down the reactions and show that they are feasible. Then finally calculate the concentration of X plus. So three parts are there. Okay. So there are two reactions, main reactions taking place. Write half reactions and balance it. Then show that they are feasible by calculating the E naught values, then finally calculate the X4 plus concentration. Okay. So reaction 1, very easy. This is A-level stuff. Delta E naught you show. Reaction 2. Okay. Very easy. Okay. So you show that they are feasible. Since delta E naught is positive, both reactions are feasible. Were you able to write that? Okay.
Yes, madam.
Very good. Then write calculation. Very easy. Okay. So you have to combine the stoichiometries. And then, okay, you can, go for a longer pathway also, but I have taken this in a short pathway with the endpoint. The relationship between A2 plus, X2 plus, and X4 plus. So this 2:2:1. So if you know the number of moles of A2 plus, half of that is X4 plus. Or you can, you after calculating number of moles of A2 plus reacted, you can calculate the number of moles of, say, Z2 plus in excess, then number of moles of, say Z2 plus reacted with X4 plus, and so on. Okay. So, okay. Number of moles of X4 plus reacted will be this. Okay? Right? Whatever the way is correct. But if you are familiar with the long pathway, okay, it is okay. Right? Shall we move on?
Okay, madam.
Okay. You go with the, I'll also try to put it in that way, number of moles of A2 plus reacted. Then it will be A2 plus reacted, number of moles of, say, Z2 plus reacted, then number of moles, that is excess, then number of moles of Z2 plus added, like that. Okay, right. Then this one. What will be the cell potential when 8 ml of A2 plus was added? Justify your answer. Were you able to do this?
Madam, is it 0.761?
Yes. No, what will be the cell potential when 8 ml? Now, how do you think? What is your thinking line? They are talking
8
about 8 ml. Endpoint is 16.
half endpoint.
Huh?
8 ml means it is half endpoint.
Half endpoint.
At half endpoint, the cell potential is equal to the cell, electrode potential of ion at the titration flask.
Correct. Very good. So you have to show that. Justify your answer. So this will be, it is a half endpoint. Okay, you don't have to write these things. I'm just explaining. If you write it is a half endpoint, enough. Okay, when you apply, then at the half endpoint, you have to tell that at the half endpoint, the say the E naught value is equal to the E naught, say the cell potential is governed by the what you have, the ion that is having this E cell is going to be, E cell of the reaction is going to be equal to the E naught cell, which is going to be equal to the, say, say half cell potential of what you have in the flask. So the titration is said, we are talking about that titration is said with A. So you have in the flask Z. So half reaction potential is this. So the potential is 7.6. Okay. So how do we expect to write that? It is the half endpoint you have to write. At the half endpoint, E cell is equal to E naught cell. Okay. At the half endpoint, E naught cell, that cell potential is totally governed by what you have in the flask, the two redox couple. You have Z2 plus and Z only. So then the half cell potential is 0.761. So at the half endpoint, it is this. Okay. It can be the other way around also. Sometimes a question can be like this. Okay. What will be the situation when the cell potential is 0.761 volts? Then what do you have to write? What is the condition there? Why do you get this? Can anybody tell? if I ask you a question, what is the situation when the cell potential is 0.761? What is the situation in the flask? Can anybody think and answer?
Half
Can
of
it,
the Z plus is reacted.
at the half-end point, concentration of reactants is equal to concentration of the product. Right? Okay. That is concentration of Z2 plus, that is your analyte. Now, before the titration, what do you have? Do you have X there? Let's look at this. Before the titration, do you have X?
No, madam.
No, only Z. Okay, Z plus is there. Okay. So when you add A3 plus, what do you get? Z plus is oxidized to Z2 plus. Okay, but do you get, A3 plus, all A3 plus is? Now, A3 plus is there, but all A3 plus is converted to what? A2 plus. Am I correct? තේරෙනවද ඔයගලන්ට? Making now I am going to add 1 drop of A3 plus. What will happen? When you add 1 drop of A3 plus, all that A3 plus will be converted to A2 plus. But Z, you have a lot. All Z plus cannot be converted to Z2 plus. But you have Z plus, out of Z plus the whole thing, small amount is going to be converted to Z2 plus. හරිද? Z plus small amount will be oxidized, but A3 plus you are adding a small amount, that whole amount will be reduced. හරිද? Got it? තේරුණාද?
Oh, madam.
So until the end point, you have Z plus, Z2 plus, but no A3 plus, only A2 plus will be there until the end point. So redox system, only one redox system will be there. Because for a redox system to be in equilibrium, you have to have both species, oxidized species as well as reduced species. But A3 plus, you have only the reduced species in the solution. But Z, until the end point, you have Z plus as well as the Z2 plus. So only that half cell potential will be governing the E cell potential, governing the potential of the whole thing. Okay, so at the half equivalence point, half end point, amount of Z plus will be equal to amount of Z2 plus, right? If you get the Nernst equation, when these two are equal only in the Nernst equation, right, that minus RT, ln products over reactants, that is going to be 1, and since it's RT ln log value, is going to be 0 because concentrations are equal. then only E cell is going to be equal to E naught of the half cell potential. So what do you have to tell when the question I ask is, what is the situation at 0.7 when the cell potential is 0.761 V? You have to tell that at 0.761 V, right, that indicates that it sets the half endpoint and the amount of Z2 plus will be, concentration of Z2 plus will be equal to concentration of Z plus. Okay, so the same thing, if you understand it well, then no problem of answering. Okay, right. Now, what is the next question? Okay, question is, I think I didn't type. The question is missing here. They are asking you to draw the. And the calculation is very important. And the yes or no?
Yes, madam.
Yes. First, draw the flask. For any titration, this drawing is very much necessary. You are talking about the titration of Z plus and A2 plus. Okay. So you have Z plus, and from the beginning, you have only Z plus, Z2 plus system, but not A2 plus and A3 plus system, because as soon as you add A2 plus, it's going to be converted to it is going to, again, it has to be, the same error is coming again. I'll correct it. Sorry, this is going to be 3 plus. Okay, so when you add A3 plus, as soon as you add, it's going to be converted to A2 plus. But so in the flask, you don't have A2 plus A3 plus system. Okay? Okay. So you don't have A2 plus A3 plus system, but you have only Z plus, Z2 plus, and A2 plus only. Okay? I'll just move again and I'll copy this, and I want to copy and show this to you. Otherwise, you understanding this is very, very important. Yeah. Just give me some time so that it's easy for you to understand. Okay. Are you with me? So this is a situation in the flask until the end point. Okay. So you have only this system, redox system, Z plus, Z2 plus. So that will be governing the cell potential until the end point. That you have to identify. Otherwise, you can't draw the titration curve. So if this is what which is going to be governed, you are starting with high potential and going for low potential. That's very important. Otherwise, you can't draw the titration curve. Okay, you have the two axes, E naught dash, units, volts, volume of, it should be 3 plus, volume of, again, I have to, sorry. Yo. Okay, volume of A3 plus added. And okay, then the starting from higher potential going for the lower potential. Okay, okay, you have to mark the endpoint and also the half endpoint. Okay, that is important. Wherever possible, mark the half endpoint as well. So what are the things? Number one, access should be correct. Without correct access, no marks. Okay, okay, these are the two axes. If the axes are correct, cell shape should be from high to low, not from low to high, other way. High to low. That you have to understand. If you don't know what is happening there, this is difficult. So that's why I'm all the time telling you to draw the flask and see what is the half reaction governing the cell potential now. Just very easy. If you have both reduced and oxidized form only, there will be uh, an equilibrium of those two governing the cell potential. So it will, if it is high, then you start with high. If it is the lower one, you start with the lower potential. Okay, you start with the high potential, the shape is correct. Then mark the endpoint, then half endpoint. Okay, so that's all about the titration curve. I think we are coming to an end. Okay, do you have any questions?
Excuse me, madam.
Yes.
Madam, මේ redox titration එකේ මේ calculation part එකේ ඒකට චුට්ටක් එතන slide එකට චුට්ටක් දාන්න යන්න madam.
Okay.
madam මෙතන මේ මෙහෙම ගන්න නැතුව දැන් අපිට මුලින් sorry Z+ මේ add කරානේ මේ 0.1 m වලින් 20 milliliter.
අපි ඒ විදියට ඉන්න මම ඒක ලියන්නම්. මම escape කරලා යන්. ඕගලන්ට පුරුදු ඒ විදියටනේ. ඒක number of
calculation එකේ අන්තිම answer එක වෙනස් වෙනවා madam ඒකයි.
ඔව් ඒක තමයි ඉන්න. අපි ඒ විදියට යන්. මේක මම අර වෙන එකකින් copy කරලා තියෙන number of moles of මෙතන A2 plus නෙවෙයි නේද?
A3 plus.
A3 plus. Okay. දකින්න. Plus reacted. Then you get the number of moles of, okay. Copy, paste, number of moles of Z plus. Reacted කියලා ලියන්න නැතුව මම reacted within brackets in excess same amount. So the number of moles of copy, number of moles of Z plus added. කොච්චරද අපි add කරේ? How many moles?
0.1 into 20 into 10 to the power minus 3.
0.1 into 20. We added 20, no?
Yeah, ma'am.
Into 10 to the power minus 3.
Yes, madam.
So number of moles of
Z plus reacted with X flow plus කියලා ගත්ත නම් හරිනේ madam.
හරි ඒක තමයි. Copy. Just give me. කීයද මේකට උත්තරේ එන්නේ?
1.2 into 10 to the power minus 3 divided by 2 madam.
0.
No, sorry, madam. 1.2
0.1. No, 1.2. Wait.
yes madam.
Is it in a 20 minus 3.05 into 20? හොඳයි. අපි උත්තරේ ගමු. එතකොට minus 3 නේ. මෙතෙන්ට එන්නේ 2 minus 0.2 නේද? 2 minus මෙතෙන්ට එන්නේ 16 into 0.05 කියන්නේ 0. 0.6.
0.8 නේ madam.
10 වරක් 9 නේ. 16
8.
into 5 කියන්නේ 5 වරක් 50 8. Sorry. 8. into 10 to the power minus 3, ne?
Yes, madam.
Okay. Thank you for showing me that. හරි
Okay,
reactor
madam.
ඊට පස්සේ concentration මේක මම ඔක්කොම delete කරලා දානවා. It will be 1.2 to 10 to the power minus p divided by v into 1000 milliliters. මෙතන
Madam.
එනකොට time වෙනවා. Yes.
Madam, මේ stoichiometry එක is x4 plus මේ z plus 1 to 2 නිසා අර අතන z plus moles ගාන හොයනකොට මේ divided by 2 එන්න
2
ඕනේ
වෙන්න
madam.
ඕන. ඔව් ඔව්. ඔව් ඒක හරි. ඒක අපිට ආවේ මේක just a minute. Okay, X and Z it's 1:2. No? Half of that divided by 1.2 into 2. I'll put it as 0.5
Okay,
divided
madam.
by 2 or 0.5. Then x2 plus 4 plus concentration will be 0.6. What is the number of moles? Sorry, what is the volume?
20 milliliters, madam.
Okay, 20. Right now?
Okay, madam.
Okay.
Yes, madam.
So this is going to be cancelled off. 0.6 divided by 20 will be Yes,
0.03, madam.
0.03. Okay, thank you about it.
Thank you, madam.
Okay, I don't know how many are there still staying. Anybody, do you, I mean,
I tried to get the same answer, madam, but when you explain it, I thought I was wrong.
all right. Because actually now that actually I quickly copied uh, another answer. This is something additional I want to do. So I copied it and it's incorrect. Now only since I did it in a rush, sorry about it. Now you know the same way. You have to calculate like all the other back titrations, same way. Okay, now? The boy who spoke now, are you okay? Now is it clear?
Okay, ma'am. Okay. Thank you,
Your
ma'am.
your voice, I mean, I
Yeah,
can't hear you
of
properly.
course.
What is your name? Is it clear for you? I can't hear you properly. Just now,
It's
it's vague
okay.
little bit. හරිද?
I got
ඔයාගේ ආන්සර් එක හරිද? ඔයාගේ ෆෝන් එක මං හිතන්නේ සිග්නල් ඉෂුව එකක් තියෙනවා. තේරෙන්නේ නැහැ. Can the others hear him properly?
No, madam. I think signal issue.
ඔයාගේ සිග්නල් ඉෂුව එකක් තියෙනවා. ඇහෙන් තේරෙන්නේ නැහැ. හරිද? ඔයාට පැහැදිලිද?
Yes, ma'am, it's okay.
ඇහෙන් තේරෙන්නේ නැහැ.
I
සිග්නල්
got
ඉෂුව
it.
එකක්. සිග්නල් ඉෂුව එකක් තියෙනවා පොඩි ඔයාගේ. පොඩක් ඔයාට මොනවා හරි ප්‍රොබ්ලම් එකක් තියෙනවා නම් ආයි එවන්න කවුරු හරි කෙනෙක් මේ ඕගලන්ගේ ඊමේල් එකේ අනික් අයට how about the others, do you have any problem, any more questions, any more sections? Silent. ඔගලන් කතා කරපු දෙන්න that boy, I don't know his name, do you have any problem? The one who spoke, Hansi, do you have any questions?
No, madam.
So far so
I
good, you have tried a lot. Good. Right. Anikaya, how about you all? Okay. Do you think it is useful if when we are doing it in this way? ඔගලන්ට මේ
Yes,
විදිය
madam.
හොඳයිද rather than doing it? I mean, this is yes or no?
Yes, madam.
Yeah. What are the good things that you see when you do it in this way?
We can check our answers with madam.
And you
In
can
the
try. We have
yeah.
given you, yeah. I want you all to try, just not to listen. Then if you come physically, definitely we will be giving you some time for you to write the answers. But online it is difficult. So we will be doing it in this way in future also. Like this, I feel it is good. So those who are interested can do and try. And definitely in the evening, in the night only, I thought of having this because then all can join. Right. But the thing is this, those who are not ready, those who are not interested, I don't know what to do. Anyway, you try your best and what to say. If you have any questions, like I told you, right, take a photograph and email that to me with your phone number. question, then I can give you a feedback. Okay, all the very best for everything. I will stop recording and hope that you are going to study this